Hello everyone, this is Chinnaiah Kalpana here. In this video, we are going to solve a differential equation from higher order linear differential equations. So let's get going. Problem. Solve d square minus 5d plus 6 into y equals to e power x sin x. Solution. Firstly, let's find order and degree of the given differential equation. Identify the highest derivative here. D square is the highest derivative, so order will be 2. And highest power of the highest derivative is a degree. Degree is 1. Or just write the given differential equation as d square y minus 5 dy plus 6y equals to e power x into sin x. We know that d is a differential operator. Then d square will be d square by dx square. Right. Now, we can write d square y as d square y by dx square minus 5 into dy by dx plus 6y equals to e power x into sin x. Here d square y by dx square is the highest derivative, so order will be 2. And highest power of the highest derivative is a degree. Degree is 1. Now coming to the problem. Given differential equation, d square minus 5d plus 6 into y equals to e power x sin x, which is an operator form. F of d into y equals to q, where f of d equals to d square minus 5d plus 6 and q equals to e power x sin x. Now we need to find the general solution to the given equation, which is given by y equals to yc plus yp. Here yc is a complementary function, yp is a particular integral. We'll find complementary function using the roots of the auxiliary equation of the homogeneous equation of the given non-homogeneous equation. Simply by putting RHS to 0, we'll get f of d into y equals to 0, which is a homogeneous equation of the given non-homogeneous equation. And we'll find yp using 1 by f of d into q. So let's begin with auxiliary equation. Firstly, we are going to find yc using the auxiliary equation. We know that the auxiliary equation of f of d into y equals to 0 is f of m equals to 0, where f of m equals to m square minus 5m plus 6. We are having f of d square minus 5d plus 6. Let's replace differential operator by m, so that we'll get f of m equals to m square minus 5m plus 6. Now, our auxiliary equation becomes m square minus 5m plus 6 equals to 0. Then, m square, we can split minus 5m as minus 2m minus 3m plus 6 equals to 0. Then, take m common from the first two terms, we'll get m times m minus 2, and take minus 3 common from the next two terms, we'll get minus 3 times m minus 2 equals to 0. If you notice, we are having m minus 2 in both the terms, so let's take m minus 2 common. We'll get m minus 2 into m minus 3 equals to 0. Now equate each factor to 0. From m minus 2 equals to 0, we'll get m equals to 2. From m minus 3 equals to 0, we'll get m equals to 3. So we'll get m equals to 2 and 3, which are real and distinct or real and different roots. Therefore, m equals to 2, 3 are the roots of f of m equals to 0, which are real and distinct. We know that when two roots say m1 and m2 are real and distinct, then complementary solution looks like c1 into 1 root into x plus another constant into e power another root into x. Now our complementary function will be yc equals to c1 e power 1 root into x plus c2 e power another root into x. Now let's find particular integral. We can find particular integral using 1 by f of d into q. We are having f of d and q, where f of d is d square minus 5d plus 6 and q is e power x into sine x. And this of 1 by f of d into e power ax into v form, we can shift e power ax towards left by replacing differential operator with d plus a into v. Later we can operator v using 1 by f of d plus a. Right? Now for just compare e power x with e power ax, then we'll get a equals to 1. Now we can find d plus a, which is equals to d plus 1. Let's shift e power x towards left by replacing d with d plus 1. We'll get d plus 1 whole square minus 5 into d plus 1 plus 6 into sine x is equals to e power x into 1 by expand d plus 1 whole square. We'll get d square plus 1 plus 2d minus 5d minus 5 plus 6 into sine x, which is equals to e power x into 1 by d square minus 5d plus 2d is minus 3d plus 1 plus 6 is plus 7 minus 5 into sine x. Right? Then yp becomes e power x into 1 by d square minus 3d plus 2 into sine x. So this is 1 by some function of d into sine bx form, right? Or the known form 1 by f of d into sine ax. We have already used this, right? So we'll use the procedure of 1 by f of d into sine ax here. Now let's find d square, which is given by minus of b square, which is equals to minus of, compare sine x with sine bx, and for b equals to 1, we'll get d square equals to minus 1 square equals to minus 1, right? Now we have to replace d square by minus 1. The denominator must be non-zero. What happens if we get denominator 0? We'll get 1 by 0 into sine x. Since 1 by 0 is undefined, so total term becomes undefined, right? Now remember that the denominator must be non-zero. Now take the denominator part, d square minus 3d plus 2, and replace d square by minus 1. We'll get minus 1 plus 2 is 1 minus 3d, which is non-zero. Since by replacing d square by minus 1, the denominator is non-zero, so we can dare to replace d square by minus 1. Right? Now yp becomes e power x into 1 by minus 1 minus 3d plus 2 into sine x, which is equals to e power x into 1 by minus 1 plus 2 is 1 minus 3d into sine x. This is equals to e power x into 1 by 1 minus 3d. If we notice, we are having 1 minus 3d in the denominator. So replace this minus with plus, then we'll get 1 plus 3d. Just multiply and divide 1 plus 3d to this fraction into sine x. This becomes e power x into 1 plus 3d is 1 plus 3d by 1 minus 3d into 1 plus 3d is 1 plus 3d into 1 minus 3d into sine x. Then yp becomes e power x into 1 plus 3d by the denominator is of a plus b into a minus b form, so we can write it as a square minus b square 1 square minus 3d whole square into sine x is equals to e power x into 1 plus 3d by 1 minus 3d whole square is 9d square into sine x, right? 3 square is 9 and d square. Again, d square appears in the denominator, so the denominator must be non-zero. Let's see what happens if we replace d square by minus 1 in the denominator. We'll get 1 plus 9, which is 10, non-zero. Since the denominator is non-zero, by replacing d square with minus 1, so let's replace d square here. Then yp becomes e power x into 1 plus 3d by 1 minus 9 into minus 1 into sin x, which is equals to e power x into 1 plus 3d by 1 plus 9 into sin x, which becomes e power x into 1 plus 3d by 10 into sin x is equals to e power x into, we can split this as 1 by 10 into 1 plus 3d into sin x, which becomes e power x by 10 into 1 into sin x is sin x plus 3d sin x. This becomes e power x by 10 into sin x plus 3 into d is a differential operator. So now we need to find derivative of sin x with respect to x. Yp becomes e power x by 10 into sin x plus 3 into derivative of sin x with respect to x is cos x, which is our required particular integral. We got yc and yp, so now let's write the general solution. The general solution is given by y equals to yc plus yp. Then y equals to yc, we have c1 e power 2x plus c2 e power 3x, and yp is e power x by 10 into sin x plus 3 cos x, which completes the problem. So we have seen a problem from higher order linear differential equations in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.